Hi students, have a nice day. In this section we are going to discuss about van der Waal equation, compressibility factor, etc. As we know that real gases deviate from the ideal behavior. This is because of two faulty assumptions made by kinetic theory of gases. Johann van der Waal, simply we can say that van der Waal, he suggested a modified equation for real gases. He considered the intermolecular attraction between the gas molecules and also the volume of the gas molecule. At a high pressure, the gas molecules do not collide with the walls of the container with the full impact. Okay, gas molecules are in random movement. They collide with each other. Also, they collide with the walls of the container. At a very high pressure, the collision of gas molecules on the walls of the container do not with a full impact, because when the gas molecules move to collide with the walls of the container, the other gas molecules pull it back. Okay, there is a drag for the collision of gas molecule on the walls of the container. Okay, when this molecule try to collide with the walls of the container, the other molecules pull back. Okay, there is a drag of collision, okay, on the walls of the container. And he corrected the pressure of the gas. P ideal is equal to P real plus A n square divided by V square. Are you clear? So Johann van der Waal corrected the pressure term. The ideal pressure is equal to real pressure plus A n square divided by V square. And A is a constant, van der Waal constant, describes the intermolecular forces between the gas molecule. Okay, gives an idea about the intermolecular forces. Are you clear? Yes. Then, similarly, we volume also corrected. V ideal is equal to the volume of the gas molecule is corrected. V ideal is equal to V minus NV, where V is the volume of the gas molecule. Okay, so two correction terms used by Johann van der Waal. And we know that PV is equal to nRT. PV is equal to nRT. So by substituting this, we get P plus, for P we have P plus A n square divided by V square. Are you clear? Yes. Into, for V minus NV. It is equal to nRT. And this equation is known as van der Waal equation for gases or real gases. Once again, the real gases deviate from the ideal behavior. Very high pressure, at a very high pressure, the gas molecules are come closer. The intermolecular forces between the gas molecule is considerable or significant. At a high pressure, the collision of gas molecule on the walls of the container with a not full impact, because when the gas molecules move to collide on the walls of the container, the other gas molecules pull it back, or there is a drag of collision on the walls of the container. And van der Waal corrected the pressure T, and the pressure of the gas is equal to, pressure of the ideal gas is equal to P real or P observed. In some textbook it is P observed. P real plus A n square divided by V square, where A is a constant, van der Waal constant, which depends the nature of the gas, that is the intermolecular forces between the gas molecule. Also it describes the tendency of liquefaction of gas molecules. Okay, it describes the tendency of gas molecule. When the gas molecule interact each other, they come closer and it condenses into liquid form. Okay, and also he corrected the volume term. Volume term also corrected. V real is V ideal is the volume of the gas molecule minus the volume of a particular gas molecule. Okay, that means B is the volume of the one gas molecule. V is total volume of the gas, then V minus NB is the corrected volume. Let's discuss the significance of van der Waal constant A and B and its unit. The van der Waal constant A and B depends upon the nature of the gas. A is the intermolecular forces, attractive force between the gas molecules, and it describes the tendency of gas to liquefy. I already told you. A is the tendency, the constant A is tendency of a gas for liquefaction or to liquefy. And its unit is A. The unit of A is atm a liter square mole raised to minus 2. Or you can write atm liter square per mole square. So that is the unit of A. And B, the constant B, it is the close packed molar volume. Okay, the close packed molar volume of the gas molecule. And hence it is the measure of molecular size. What is B? B is the measure of molecular size. And the unit of B is a liter mole inverse, or you can write that liter per mole. Okay, so that's about the van der Waal equation. From this equation we can determine the equation for 1 mole of gas, 2 moles of gas, etc. Okay, I write one examples. For 1 mole of gas, the equation is, for 1 mole of gas, the equation is P plus A by V square, because N, 1 square is 1 itself, into V minus B. N is equal to 1. For 1 mole of gas, N is equal to 1 and is equal to RT. Are you clear? Sometime application question is asking. Then what about 2 moles of gas? For 2 moles of gas, N is equal to 2. So P plus A, 2 square, that is 4. So we can write that 4A. Okay, 4A divided by 4A divided by V square into V minus 2B. n is equal to 2, so V minus 2B is equal to 2RT. Okay, so this is the van der Waal equation for 1 mole of gas. This is for 2 moles of gas. Similarly, you can do it half moles, 0.25 moles, 0.1 mole, 5 moles, etc. Are you clear? Yes, next we discuss the compressibility factor. The deviation of real gases from the ideal behavior is measured in terms of compressibility factor Z. And Z is the ratio of product of pressure or volume to nRT. Okay, so what is Z compressibility factor? Z is equal to PV divided by nRT. Okay, so what is Z compressibility factor? It is the ratio of product of pressure volume to number of moles and temperature. Or we can easily say that Z is equal to PV divided by nRT. For ideal gas, Z is equal to 1. Okay, for ideal gas, Z is equal to 1. For real gas, Z is either greater than 1 or Z is less than 1. Okay, let's draw one plot. Here the compressibility factor is at PV divided by nRT. And it is 1 for ideal gas. Okay, you said 1 for ideal gas. 0.8 is 0.8, 0.6, 0.4 and 0.2. This is 0. Okay, here in the x-axis we take pressure in barometer. 200, 400, 600, 800 and 1000. Okay, pressure increases in the x direction and the PV is equal to, Z is equal to PV divided by nRT increases in the y-axis. 1.2, 1.4, 1.6, etc. Okay? And we know that different gases having different tendency, different nature. Okay? So, some gases having Z greater than 1, some other gases having Z less than 1. Okay, hydrogen. Hydrogen, pressure increases, Z also increases. The compressibility factor Z also increases. For nitrogen, the change is like this. So this is for N2. Okay, this is for N2. Then oxygen. Oxygen slightly decreases, then increases. O2 initially decreases, reaching a minimum, then it is increases. Another is methane. For methane, first decreases with the increase in the pressure, then it increases. CH4. For carbon dioxide, okay, for carbon dioxide, initially it decreases and reaching a minimum, it increases. For some gases, the Z is always greater than the 1. Okay, for some gases, Z is greater than 1. And that is called a positive deviation. A deviation from the ideal behavior, it is positive deviation from the ideal behavior. Okay. The gases such as hydrogen, helium, nitrogen, etc. they have positive deviation. Are you clear? Yes. Then the gases like O2, oxygen, dioxygen, methane, carbon dioxide, these are negative deviation. Initially they have negative deviation. As pressure increases, the Z compressibility factor Z decreases, reaching a minimum, then it increases. Are you clear? So Z is either greater than 1 or less than 1. Z is equal to 1, it is ideal. Okay, the nature of the gas is ideal nature. When the gas behaves ideally, at a very high temperature and low pressure, the gases behaves ideally. It is nearly, the pressure is 0. Look at this point. Okay, if the pressure is nearly 0, the gas behaves ideally. So when real gases behaves ideally, at a very very low pressure and a high temperature, the gases behaves ideally. And one another point, boil point or boil temperature. Boil point or boil temperature. Not boiling temperature, that were different concepts. Boil temperature. The gases which obeys ideally, the temperature is called a boil temperature. Okay, what is boil temperature? The temperature at which real gases behaves ideally is called a boil temperature or boil point. And that decides the liquefaction of the gases. Okay, are you clear? So what is boil point or boil temperature? The temperature at which real gases behaves ideally, that temperature is called boil temperature or boil point. Are you clear? Yes. Then the compressibility factor also relates in the volume, real volume as well as in the ideal volume. What is compressibility factor? This plot is very important, you go through it. What is compressibility factor? Okay, I just erase these things. What is compressibility factor? Compressibility factor Z is equal to P V real divided by nRT. V real by nRT. Also, PV is equal to nRT. So here the volume is ideal. Okay. PV is equal to nRT for ideal gas. It gives more insight to the compressibility factor or the volume of the gases. Yes. Then what is V ideal? V ideal is equal to nRT by P. Okay, V ideal is equal to nRT by P. Let's rearrange this equation. Z is equal to V real divided by nRT by P. Okay, it's reciprocal. Or simply you can directly write that by applying this into that, you can easily understand that the reciprocal of this term is this one. So Z is equal to V real divided by V ideal. Okay. Simply you can understand that V ideal is equal to nRT divided by P. By taking the reciprocal you get P divided by nRT. Also you take the reciprocal here. So it becomes 1 by V ideal. So this is another relation for compressibility factor. Compressibility factor Z is equal to V real divided by V ideal. Okay, so that's about the van der Waal equation and the compressibility factor. Okay, let's discuss some basic concepts about the liquefaction of gases and liquid phase. First one, liquefaction of gases. When we apply pressure on decreasing the temperature, okay, while decreasing the temperature and applying the pressure, the gas molecules come closer and it tends to liquefy. Thomas Andrews studied these things and he found that in the case of carbon dioxide, 31.1 degrees Celsius, its critical temperature. Above that temperature, the gas cannot be liquefied even we apply high pressure. Below that temperature, the carbon dioxide liquefy by applying pressure. So that temperature is called critical temperature. Once again, when we increasing the pressure or by applying the pressure and lowering the temperature, the gas tend to liquefy, because when a high pressure is applied, the gas molecule come closer, and by decreasing the temperature also, the attractive force increases and the gas tends to liquefy. Thomas Andrews studied the carbon dioxide. An isotherm was he studied. At 31.1 degrees Celsius, the carbon dioxide gas and the liquid carbon dioxide coexist. And that means above that temperature, okay, the temperature is 31.1 degrees Celsius. Above that temperature, the carbon dioxide gas cannot be liquefied. Below that temperature, the gas can be liquefied. So what is critical temperature? The temperature at which the gas can be liquefied by applying pressure. Above that temperature, the gas cannot be liquefied. And the critical temperature is denoted by Tc. Okay. Higher the critical temperature, the more easily the gas can be liquefied. Remember that? Higher the critical temperature, more easily the gas can be liquefied. Okay, in the case of carbon dioxide, the critical temperature is equal to 31.1 degree Celsius. Also you can convert into the Kelvin scale. And next is PC, critical pressure. The minimum pressure is applied to liquefy the gas at its critical temperature is called critical pressure. What is critical pressure? The minimum pressure, or simply the pressure is applied to liquefy the gas at its critical temperature is called critical pressure. And next is critical volume. The molar volume. The volume of 1 mole of gas at its critical temperature and critical pressure is called critical volume. Okay, so these things are deleted from the syllabus. Anyway, you just understand that liquefaction of gases. Next is liquid phase. Liquid, we know that liquid has definite volume, but not definite shape. Okay, the shape of the liquid is the shape of the vessel in which it is kept. And some other properties are for liquid stage. First one is vapor pressure, second one is boiling point, then surface tension, viscosity. I briefly explain one by one. First one is vapor pressure. What is vapor pressure? The pressure exerted by the vapors on the surface of a liquid when the liquid and the vapors are at equilibrium. Okay, when we take a liquid in a vessel, in a closed vessel, and it tends to vaporizes. Vaporization and condensation. Okay, vaporization and condensation. And the pressure is measured by a manometer, the pressure gauge. So what is vapor pressure? The pressure exerted by the vapors on the surface of a liquid when the vapor and liquid are in equilibrium. That means the rate of vaporization is equal to rate of condensation. That is vapor pressure. Vapor pressure. Okay. Vapor pressure. The vapor pressure depends upon the factors. One, the nature of the liquid. Second one is the temperature. Okay, mainly nature of the liquid and the temperature. The more volatile liquid has more vapor pressure. Okay, if the liquid is more volatile, the vapor pressure is more. Next, second factor is temperature. Temperature increases, the molecule get kinetic energy and the tendency of vaporization increases. That's why vapor pressure increases. So temperature increases, vaporization increases, and vapor pressure also increases. Are you clear? Yes. The next term is boiling point. As earlier, boil point. Here, boiling point. Okay, boil point and boiling point is different. Boil point is the temperature at which real gases behaves ideally. Boiling point is the temperature at which the vapor pressure of the liquid becomes equal to external pressure. When the vapor pressure is equal to external pressure, the liquid starts to boil. In lower classes you study the temperature at which the liquid boil is called boiling point. Yes, correct. In that classes enough. But now you understand that boiling point is the temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure or external pressure. At a high altitude, the external pressure, the atmospheric pressure is low and the liquid boils fastly. And cooking is difficult at the mountain tops. And that's why pressure cookers are used. You just understand that. Okay. That is about the boiling points. Then next is boiling point of water. Two types: normal boiling points and standard boiling points. Normal boiling point is expressed in atm. Okay, when the pressure is 1 atm, the boiling point is called a normal boiling point. For water it is 100 degrees Celsius. What is the normal boiling point of water? It is 100 degrees Celsius. In standard boiling point, the pressure is in barometer. Okay, at a sea level, the pressure is 1 atm. So, in barometer, the boiling point of water is 99.6 degrees Celsius. Okay, that's the difference. Normal boiling point is the boiling point at 1 atm pressure. Standard boiling point is the boiling point at 1 barometer pressure. Are you clear? Yes. Then next is surface tension. Okay, you go through it. The molecule, you already learned this. The molecule at the surface under tension because of the downward pull and the sidewise pull. Okay. The molecule in the bulk is attracted in all direction, but the molecule at the surface attracted by downwards and sideways. The molecule at the surface is under tension. This is called the surface tension. According to the definition, it is the tangential force acting on the surface. You just understand what is surface tension. Due to surface tension, liquid adopt a spherical shape. Okay, liquids adopt a spherical shape. Remember that. Next is viscosity. The liquids flows layer by layer. One layer slides of the others. One layer slides the other. So this, due to this sliding, the movement of layers are pulled by the other layers, and that force is called viscous force. So viscosity means the flow of liquid layers pulled by the other layers. Okay, temperature increases, viscosity decreases. As we compare the oil, water, honey, honey is more viscous than oil than water. Okay, you can make an experiment. You take a glass plate, put a 3 drops, 1 drop of water, 1 drop of oil, 1 drop of honey, and just tilt it. You can see that water drops move very fastly, oil drops slowly, honey mostly stick on there because honey is more viscous than the oil, is more viscous than the water. And remember that all these things is deleted from the syllabus. You just understand that, go through the topic, any doubt you can ask. So this chapter is finished, successfully finished. In the next section we will start a new chapter. Thank you.